Time travel. It's the stuff of dreams, isn't it? Imagine stepping into a machine and being whisked away to ancient Egypt or the distant future. What would it be like to witness historical events firsthand or glimpse what's to come? Time travel has captivated our imaginations for centuries, appearing in countless books, movies, and TV shows. But is it truly possible? Could we one day build a time machine and bend the rules of time itself? The concept of time travel is deeply intertwined with our understanding of time itself. We experience time as a linear progression, always moving forward. But what if time isn't a straight line, but rather a winding river, bending and looping back on itself? What if, just like we can travel through space, we could also navigate the currents of time? The laws of physics, as we currently understand them, don't necessarily prohibit time travel. In fact, some theories suggest that it might be possible, albeit incredibly challenging. To grasp the complexities of time travel, we need to delve into the mind-bending world of Albert Einstein and his groundbreaking theory of relativity. Albert Einstein, the iconic physicist, revolutionized our understanding of space, time, and gravity. His theory of relativity, put forth in the early 20th century, provides the foundation for much of modern physics and offers intriguing possibilities for time travel. One of the key takeaways from Einstein's work is that time is not absolute but relative. It's not a universal clock that ticks at the same rate for everyone, everywhere. Instead, time is flexible, like a fabric that can be stretched or compressed. Imagine a giant trampoline as a representation of space-time. Now place a bowling ball in the center. The bowling ball represents a massive object, like a star or a black hole. Just as the bowling ball creates a dip in the trampoline, massive objects warp the fabric of space-time. This warping is what we experience as gravity. The greater the mass, the more extreme the curvature. Here's where it gets interesting for time travel. As gravity warps space-time, it also affects the flow of time. Time slows down in stronger gravitational fields. This phenomenon, known as time dilation, has been experimentally verified. Clocks on Earth's surface, for example, tick slightly slower than clocks on satellites orbiting farther away from Earth's gravitational pull. If the fabric of space-time can be warped and stretched, could we potentially fold it onto itself, creating shortcuts between distant points in space and time? This is where the concept of wormholes comes into play. Imagine an ant crawling on a sheet of paper. The ant has to travel across the entire sheet to reach a point on the other side. But what if we folded the paper in half, bringing the 2 points close together? The ant could then take a shortcut through the fold. Wormholes, theoretically, would function in a similar way. They would be tunnels through space-time, connecting 2 distant points, potentially even different points in time. While wormholes remain highly speculative, they are permissible within the framework of Einstein's equations. However, creating or even finding a wormhole would be an immense challenge. They would require exotic matter with negative mass-energy density, something we haven't yet observed in the universe. While time travel still lies firmly in the realm of science fiction, the possibilities it presents are both exhilarating and perplexing. If we could journey through time, we could potentially alter the course of history, prevent disasters, or even meet our past selves. However, time travel also raises a host of paradoxes that challenge our understanding of causality and the nature of reality. One of the most famous is the grandfather paradox. Imagine traveling back in time and accidentally killing your grandfather before your parent was born. If your grandfather never existed, how could you have been born to travel back in time in the first place? These paradoxes suggest that there might be fundamental limitations to time travel, or that our understanding of its mechanics is still incomplete. Perhaps there are mechanisms in place, yet unknown to us, that prevent such paradoxes from occurring. Or maybe time travel is simply impossible, and the universe has safeguards in place to protect the integrity of cause and effect. Despite the challenges and uncertainties, the allure of time travel continues to drive scientific inquiry and fuel our imaginations. As we delve deeper into the mysteries of the cosmos, perhaps one day we'll unlock the secrets of time itself.